Hello, today we're going to be talking about geometric sequences. A geometric sequence has a starting value A, and if it has a common ratio R, then it's going to have this form here, where the first term would be A, second term is A times R, then A times R squared, and A times R cubed. We have both a recursive definition and explicit definition for those. Again, remember, for the recursive definition, you need that initial condition statement. What is the first term equal to? And then the second part to the recursive is saying how to get a sub n from a sub n minus 1. And for geometric, that's fairly simple. You just multiply by that common ratio. In the explicit form, again, works out very well. You just have the first term here, the common ratio to the n minus 1 power. And again, it's n minus 1 because, again, the first term is not multiplied by r, the second term is multiplied by r to the first power, and the third term by r to the second. So that's why we have n minus 1. And again, the condition that that's only for n values greater than or equal to 1. So if we take a look at this example, trying to determine, first of all, is the sequence geometric, and if it is, what's the first term and what is the common ratio? So our sequence being 3, 6, 12, 24, and 48, what we look at is take and divide the second term by the first term. Well, that's 6 over 3, and then the third term by the second term, that's 12 over 6, and so on. Find all those ratios. Well, the common ratio is 2. So that means that yes, it is geometric, and then the first term is a sub 1. And so that's what we're looking at there. Again, if we were to write either recursive or explicit forms for that, or actually do both, the recursive would look like this: a sub 1 equals 3, a sub n equals a sub n minus 1 times 2. So that's all we have for the recursive. And for the explicit form, it is just a sub n equals the initial value 3 times 2 to the n minus 1 power. So again, you can see the difference there between recursive and explicit. Notice, though, the similarities. Again, first term for the recursive is here, for the explicit is here. Common ratio here for recursive and here for explicit. Notice they both actually have an n minus 1 in them. So very similar there. Looking at another sequence, 3, 6, 9, 12, 15. Looking at those ratios, they are not the same. Okay, the ratios are different, so there's no common ratio, so that is not geometric. A third sequence, notice it's a little different here. 3 to the 5th, 3 to the 10th, 3 to the 15th, and 3 to the 20th power. And again, we're not even necessarily figuring out what those are, but if we find those ratios, they all turn out to be 3 to the 5th power. So that is a geometric sequence. Again, a common ratio of 3 to the 5th, and actually a first term of 3 to the 5th as well. So notice, again, they're both the same, and there's nothing mathematical about that. Just happens to be that that's the first term and the common ratio. Here are a few problems for you to try, just again determining if the sequence is geometric, and if it is, what is the first term and the common ratio. And again, you might also, just for extra practice, try to write a recursive and explicit form for these, if they are geometric. So you can go ahead and pause the video and then resume, and I'll go through these three problems. So in this first one, 4 divided by 2, and 8 divided by 4, and 16 divided by 8. Those all equal 2. So yes, it does have a common ratio, so it is geometric. Recursive form for that would be a sub 1 is 2, a sub n is a sub n minus 1 times that common ratio of 2. So again, just kind of happens that they have the same starting value and common ratio. The explicit form for that would be a sub n equals 2 times 2 to the n minus 1 power. So again, this first 2 is the initial value 2, second one is the common ratio 2, so a little bit different there. Looking at the second one, 5 divided by 1 9 divided by 5, those are not the same. So it is not a geometric sequence. And again, once I find two ratios that are different, I do not need to continue. And then the third one, 2 to the 7th divided by 2 to the 3rd, 2 to the 11th divided by 2 to the 7th, and 2 to the 15th divided by 2 to the 11th, all equal 2 to the 4th power, which would be 16. In this case, I kind of prefer the 16 rather than the 2 to the 4th power. So we could write a recursive formula for that. A sub 1 is 8, and again that's 2 to the 3rd power is 8. A sub n would be a sub n minus 1 times 16, because again that's that common ratio. The explicit form would be a sub n equals 8 times 16 to the n minus 1 power. Alright, so we have a geometric sequence here, 4, 12, 36. They are asking what the 10th term of the sequence is. So we would be probably looking at finding a explicit form, although 10th term wouldn't be so bad as far as finding the recursive way to figure that out. We would want to figure out the common ratio. Again, they do tell us that it is geometric, so we really only need to check one. 12 divided by 4 is 3, so that is our common ratio. The explicit form would be a sub n equals first term of 4 times ratio of 3 to the n minus 1 power. Again, the key here is to remember to do the n minus 1. Occasionally people forget that, so a sub 10 would equal 4 times 3 to the 9th power. And for now I'm just going to leave it like that. You could certainly use a calculator to figure out what that would actually equal, but I'm just going to leave that there for now. The second one, now we've got second and third terms of this geometric sequence are missing. So we've got 2 blank blank negative 54. And again, they give us the first term and the fourth term. This is very similar to how we handled the same sort of problem in arithmetic sequences. This term here would be 2 times r. This would be 2 times r squared. And the negative 54 would be 2 times r cubed. So that gives me an equation, 2r cubed equals negative 54. So I can divide by the 2, I get r cubed equals negative 27. Then I can cube root both sides and figure out that r is negative 3. So seeing that r is negative 3, then I can figure out the a sub 2 and a sub 3 in this pattern. So a sub 2, and again I'm more or less doing this recursively, a sub 2 would be a sub 1 times the constant ratio of negative 3. So a sub 2 is negative 6. Since I know a sub 2 is negative 6, I can find a sub 3. It would be negative 6 times negative 3, which would be a positive 18. And I can double check to make sure that my pattern appears to work by multiplying the 18 by the negative 3 in order to get negative 54. So here I have a similar type of problem. It's only the second term that is missing though. So again, you can go ahead and give this one a shot, so you can pause it, and then when you resume I'll go ahead and go through it. So we have a missing term there. They do tell us that it is a geometric sequence, so we know that that missing term would be 3 times that common ratio, and the 12 would equal 3 times r squared. So we could divide by 3 and figure out that 4 is the r squared. And then we could square root both sides. Now this gets a little tricky because when I square root both sides, maybe let me do this properly actually. So when I square root both sides, the one thing that I have to remember is that I can really have a positive or negative here. And so it turns out that my ratio could either be a positive 2 or a negative 2. Now this wasn't an issue on the previous one because we had 2 missing ones and everything was positive. So really a negative couldn't have come into play there. Whereas here, this middle term could either be positive or negative. So really, the second term there, a sub 2, could either be a positive or negative 6. And I'm getting the 6 by just doing the 3 times the positive or negative 2. So that's where it's either a positive or negative 6. We don't know for sure with that missing term in that geometric sequence. Alright, here we've got a ball bouncing problem. So we've actually done similar things like this with our exponential modeling equations. So geometric sequences are a little bit different way to handle this. And so what we would want to look at for this one is coming up with a probably explicit formula for this in order to find the height of the 10th bounce, I would say. And again, 10th bounce, it wouldn't be so bad to use recursive, but again, it's right on that edge where I would probably lean towards using explicit. So we have a first height of 100 centimeters and a second height, a third height of 49. So really I'm looking at a sub 1 equals 100 and a sub 3 equals 49. So if I go to find my ratio, I know that the initial value, or let's start with this middle one, this would be 100 times the ratio, and 100 would be or the 49 I should say would be 100 times the ratio squared. Again, that gives me an equation that I can solve. 100r squared equals 49. And so I can divide by 100. Now, it might be tempting to actually do that division, but because we're going to square root, I would say just leave that alone for now. We square root both sides, and we get the square root of 49 100ths. And so the ratio is actually 7/10. Now, notice when I square rooted that time, I did not have to consider the positive and negative. That's because the ball is not going to travel through the floor and then back up. So the negative does not make sense there. So I know that the ratio is 7/10. That allows me to write a formula for that. So a sub n would equal the initial height, bounce height of 100 times 7/10 to the n minus 1 power. So again, here looking at this, we have our formula, and we could plug a 10 in to find the height of the 10th bounce. So a sub 10 would actually equal 100 times 7/10 to the 9th power. And again, I'll just leave that as it is. You can use a calculator to figure out that height. And then eventually they ask for the 6th bounce as well. So a sub 6 would equal 100 times 7/10 to the 5th power. And again, that's because you would do 6 minus 1 for the exponent. So, well, hopefully this was helpful and made some sense. So, thanks for watching.